So now, next we're going to do some property table questions. So I'm going to look, I numbered each line here, and I always break down my question into my knowns and my unknowns. So if you look at the first line, my temperature is known. My temperature, I'm at 300 degrees C, and U is total internal energy. I don't know that we've talked about this yet. U is total internal energy. X is quality. I'm just going to specify these just to make sure we're all on the same page here. So the first question, I'm going to look, my temperature and my total internal energy, U, is given. So now I'm going to look, we know that we're dealing with water here. There's another question about the refrigerant, and we'll discuss it after. Water. So if I look at my table here, my 300 line is here, temperature, pressure. So my knowns are temperature and U. So I'm going to look at my values of U, these three here. And what you'll notice is that U is equal to UF. This question is for picking out different kinds of points on the graphs. So if I look here, U 3,333 is equal to my UF. What does that mean? That means that my point is a saturated liquid. And so I am at, if I sketch my graph here, hang on. There we go. If I sketch my graph here, let me go down here. I'm at this point right here. I'm right at the saturated liquid point where my water will start to boil. So U is equal to UF. Therefore, I like to use some of the math lingo, the triple points for therefore. Therefore, P is equal to P sat. My pressure is equal to my saturated pressure. Because remember that these lines, the lines that we exist on are constant for a constant pressure, right? So my pressure is my saturated pressure, which is given over here. It's 8.581 MPa. And my phase, what phase am I in? That's pretty easy. It's written right in the table. I'm at saturated liquid. Next question, a little bit more challenging this time. So if I look at the next question, I have my temperature at 150 and my value of U. Oh, I'm just gonna point of where I'm getting these tables. So right now, because my temperature is what's given, let me open it in the correct screen so you guys can see. Because my temperature is what's given, I'm going into my property tables. We know it's temperature and we know the fluid is water. So I'm going here, saturated water temperature table. This is where I'm working. These are screen caps I'm taking out of these tables. Normally what you would have to do, you flip through the table, you look, you'll say, I know I have temperature, so I'm going to take the saturated water temperature table and I'll go through until I hit the temperature that my water is at, okay? So I'm just taking screen caps out of those tables. So I have my temperature, and if I look, and I have a value of U given. So if I look here, these are my three values of U. What you're going to see is that U is between, if you look at UF and UG, UF for liquid, UG for water, the value of U, which I was given, which is 1,595, is between these two values, okay? So therefore, so the value of U I have is between UF and UG. What does this mean? This means that I'm in a mixture. That I'm over, if I open up my table again, I'm at a mixture. I am over here in the saturated liquid vapor region. I don't know exactly where I am. I don't know what quality I have. I don't know where I lie on the line, but I know I'm in there somewhere. Okay? So now, part of the question is to determine the quality. And how are we going to do that? So there's a nice little equation. So there are a couple of different ways we can look at this. The quality we know that the quality can be defined as the mass of the gas over the total mass. But I don't know the mass of the gas. I don't know how much there is in the system. And I don't know the total mass either. So for right now, this is not all that useful. I can't solve it this way. What I can do though, is I'm going to look at my values for UF and UG. So the way that we're going to solve it, its derivation is in your notes. I'm not going to go through how it's derived exactly, but it's from the equation of a straight line. So I'm going to Y to represent any one of these properties. Y can be used for any one of these properties here. So Y is good for specific volume. It's going to be good once we get there's enthalpy. It's good for U, which is what we're doing now, total internal energy. It's also going to be valid for S, for entropy once we get there. It's going to be valid for any one of those properties that are changing. And it's going to be equal to YF, so the value of the saturated liquid, plus our quality, times the value of evaporation. And in case you guys didn't know, the property YFG is equal to, let me just take a quick peek in the table, is equal to YG is equal to the value at G minus the value of F. This essentially describes the evaporation. So it's going to be, so this is the value for evaporation. So if you look at this, if you want to read the equation sort of out loud and like in words, it's basically what you're looking at is the value of the water, how much gas you have, oops, times the values for evaporation. This makes a little bit more sense, but right now we're talking about total internal energy, U. So basically I'm looking at the total internal energy of water, how much water I have, times how much energy it takes to evaporate the water. So if you look at the equation that way, it makes a lot of sense. It's sort of intuitive. It's derived, of course, from the straight line, but we're not going to go through that here. It's in the notes if you're really curious. Give myself a little bit more room. So if I look at what's given to me, let me just write this equation down for values of U. So U is going to be equal to UF plus X of UFG. I need more room than that. Okie dokie. If I look at what's given in the question, I know U. What I'm given is the total internal energy of my substance. UF, I can get out of the table. UG, I can get out of the table. X, I don't know. So I can solve for it. So if you go through the table, if you scroll here, can I scroll enough to include it in the frame? Okay, I'll have to scroll back to right, but you can see here the numbers. I have my UF of 613.68 and my UFG of 1,927. So if I do the math here, U is given. UF I got out of the table. X is my unknown And then UFG again was taken out of the table, which will give me a value of X of 0.5. Just keep in mind, U has a unit of kilojoules per kilogram. My bad, kilojoules per. And X is unitless. It's a ratio, right? So it's just X is equal to 0.5, 0.5. And so what does that tell me? Because I have a quality, I'm just going to copy this graph and we'll look at it after. But we know that I'm in this area, in the saturated liquid vapor mixture. In a saturated liquid vapor region, which means that we're talking about a mixture. So I have my value of X, my phase, mixture. And because I'm on that, that pressure line, those pressure lines don't change, right? I'm keeping it at a constant pressure. My P is equal to PSAT, which is 0.4758 MPa. All right, so question 3. In this question here, I'm given pressure. Put my tablet back in. I'm given pressure and quality this time. Those are my knowns. Okay, the tablet's working. All right, so I'm given pressure and given quality. So in the previous question, I was looking at temperature tables because I was given values of temperature. This time I am not. I'm given values of pressure. So instead, what we're going to do is we're going to open up the pressure tables, which I screen capped here. So my pressure here, 250 kPa. Oh no. Did I screen cap the incorrect pressures? Okay, no, I did not. What happens is if you look at these pressure tables, just to be careful, I almost caught myself here. The pressures here, the top of the table lists them pressure kPa for small values, and then it jumps pressure MPa and it starts listing larger values. So just make sure you're looking at the right lines and you're in the right units. Because this question is given 250 kPa, which is equal to 0.25 MPa, and that's how it's written in the table. The header isn't accurate right here. Let me just fix that. It's MPa at this portion of the table. So given that my quality is known, I know the phase has to be a mixture. That's the mixtures are the only phase with quality. Compressed liquids and superheated vapors don't have a quality because they're pure liquids or pure gases. So just by knowing by virtue of having an X, we know we're a mixture. It has to be. All right. So that's one part of the question asked. The temperature, because it's a mixture, we're going to have to be at the saturated temperature, given right here. So we know that T is Tsat, which is going to be 127.44 degrees C. And then how am I going to find U? I'll use the same equation I used before. UF plus X UFG. This time, however, X is known. I'm not searching for it, it's known. UF and UFG, I'm going to get out of the tables. Over here, UF and UFG. Actually, I don't need UG. UF and UFG are right here. 535 and 2002. So the math here is going to be very straightforward. Use F was 535.1. X is at 60% or 0.6, and then UFG 2002. Which gives me a value of U of 1,736.36 kilojoules per kilogram. Don't forget your units. The units will become more important as we do more involved problems, but it's a good habit to write them down. Now, if I look at pressure number 4, I'm going to look over here, my pressure table, 600 kPa, which is 0.6 MPa. So this is MPa over here. If I look at my value of U, my value of U is 2,567 for UF. So my saturated vapor will be at that enthalpy. Sorry, not enthalpy, at that in total internal energy. What do I notice is that it's larger than my value of U. So UF is larger than U. What does that mean? It means that I'm a superheated gas, okay? I'm no longer in the mixture phase. That I'm a superheated gas. And so this table here is no good. Let me take red. This table is no good because I'm not saturated. I'm superheated. Knowing that I'm superheated, I'm going to have, there's no quality because it's pure gas. So there's no value of X, no quality, or no value of X. So what you're going to have to do in this case is you're going to go find you keep scrolling, you'll find superheated tables, and they're organized by pressure and temperature. So you'll see here I have pressure and for each pressure, I have different saturation temperatures. All right, so for this one, it said that I was at 0.6. And given my value of U, oh, I didn't write the units on top. What were the VUHS? Okay. So they're up here. So it's V, U, H, and S. So specific volume for V, U total internal energy, H enthalpy, S entropy. So if I go down my values of U, I'm going to find, oh, look, very conveniently, for the sake of the question, 2,477 is on the table. And if I backtrack here, if I go this way, I'll find my Tsat. So I know that this total internal energy occurs at 700 degrees C. Next question here, I have temperature and pressure. I'm looking, which is a little bit unusual because as we saw earlier, right, temperature and pressure are not independent of each other. They're very, very closely linked. But I have my temperature, and if I look at my pressure, you're going to see that we're very, very, oh, it's because I got the units are backwards here. So MPAs is, so there's 1,000 kPa in 1 MPa, which means if I move this over by 3, I'm at 19,940 kPa. Okay, that's where we're at. I just got the numbers backwards in my head. So if you look at this, you're going to see that P is much, much, much smaller than PSAT. What does this mean? This means, yeah, my pressure is much, much, much smaller. Yes, my pressure is smaller than PSAT, which means that we are a supercooled liquid. So if I look back at, can I copy paste it? Nope, I can't. Okay, but if I can scroll, it means that we're over here in the compressed liquid region. We're over here somewhere. And as I said earlier, we're always going to take, for the compressed liquids, we're going to take it from the temperature table. So they're looking for my value of U, which is going to be approximately equal to UF. So therefore we're compressed. And U is approximately equal to UF, which is 251.1. You must always take the values from the temperature table. No, I think my unit, no, there's something funky with these units here. One sec. Temperature. 60. Ah, okay, there we go. Something, it felt wrong, here we go. So this unit is not an MPa. This is KPa. I'm sorry, I'm cropping the headers incorrectly, which is leading to confusion. That's my mistake. If I crop it correctly here, you'll see that the pressure is 60 kPa. 60 degrees C is in kPa. There we go. I knew something felt funky. There we go. That was very much my mistake. I apologize. All right, let's there, this makes a lot more sense in my head. So the pressure, if I look at 60 degrees C and my pressure here of 19 kPa, which means that in order to have to be saturated at this point, we need a pressure of 60 degrees C and 19, almost 20 kPa. And my pressure is much larger than that, right? My 200 kPa is much larger than 19.4, which means that my water here this is water, is under high pressure and then relatively low temperature. We're not adding a lot of heat, so we're at low temp. And these two factors combined together, therefore, we are at a compressed liquid. Basically, we haven't either reduced the pressure enough to be able to boil the water, or we haven't increased the temperature enough to be able to boil the water. Sorry for the confusion there with the units. That was my mistake. Okay, this is the last question from the table. So here, again, I have pressure and temperature, which is a little bit strange because we know they're not independent of each other, right? They're not independent units. And you cannot take pressure and temperature to your pressure or temperature tables. Okay, you'll get nowhere. Because if I try to take it to a temperature table, I have temperature, no important values, and then nothing I can do with the math with the pressure. So it's sort of a clue that we're going to be in the superheated phase. Because those tables are reliant on both temperature and pressure, and lo and behold, it is true. So if I find the, we're at 1,200 kPa, which is 1.2 MPa over here. And the temperature we're given is 370. And 370 is unfortunately not on the table. We have 350, 340. So I'm going to go somewhere in the middle, which means that my total internal energy, which is what I'm asked to solve for, is going to be somewhere in between. What we're going to have to do then is, which means we're going to have to interpolate the values. We can answer part of the question. We know that it's our phase is superheated gas. Therefore, there's no quality. And in order to find our values of U, I'm going to interpolate between T, 350 degrees C, which gives a value of U 2,872.2, and a value of T, 400 degrees C, which is a value of U equal to 2,954.9. All right, so I'm going to interpolate between these values like I showed you earlier. I like to do similar triangles. So the y2 minus y1 over x2 minus x1 is equal to the same thing. So I'm going to do my y2, 400. So this is like, I'm treating them as, these are my values of y and these are my values of x. You can set the table up. You can switch it because it's a ratio. You can switch them up. So I'll just show you a couple of different ways of solving it. You could do y2 minus y1 over x2 minus x1, which is how I chose to do it. So 400 minus 350. Sorry, ooh. No. 5. Oh, yes, okay. So there are a couple of different ways of doing it. Okay, we'll start with this one. So y2 minus y1 over x2 minus x1. So I'll just label them here. So we'll call them x1, x2, y1, y2. You can rearrange, because it's a ratio, in a couple of different ways. All right, so y2 could be this one. y2 minus y1 over x2 minus x1 is equal to y2 minus our unknown minus our unknown, which is u, divided by, which is our, and then I will write it again in here. Let me just, hold on. I want to make sure this is how I'm writing these ratios is clear, because there are lots of different ways of doing it. There are tons and tons and tons of ways of organizing this. And then I have a value of t equal to 370, which is my u unknown. So you can structure it this way. I like to structure it where I can also restructure it this way, where it's the difference, my differences in temperatures is equal to my differences in pressures. This one here is sort of from the similar triangles equation of a line. This one here is temperature on one side, total internal energy on the other side. But you see, if I rearrange, basically all I did is I multiplied by and divided by that on both sides. So the equations can be rearranged many different ways. You can try writing it different ways just to check. Make sure you're comfortable with this before you continue with the course, and you can come with me with any questions on Friday. But it's important that you get this straight. This is we're going to be doing a lot of interpolation in this class, so just make sure that you can structure these equations properly. And if you isolate your value of u, you're going to get 2,905.28 kilojoules per kilogram.